Poisson regression in R is very easy. You just fit GLM. You just want to make sure the family equals Poisson. The log link function is the default link function. And you can just add the plot with an AB line statement. Oh, I'm sorry, AB line, that's for the linear model. And then lines, Jeff grabbed the actual X and fitted Y values and then colored that in blue. Okay, so the GLM fit is in blue and the linear model fit is in red. Okay, and notice the GLM fit is of course nonlinear, right? Because it's linear on the log of the mean scale, so so that's why it's a little curved there. But you can see the fit is pretty similar. Okay, so there is some concern over the mean variance relationship in this data set. So here you can define a generalized form of residual. These make more sense the larger the actual means are. So it's kind of hard if you were to, for example, in a GLM do binary regression. The residuals always look kind of funny, but as whatever process you're studying, if it looks more Gaussian, like in the Poisson case, if you have larger counts, then the residuals look okay, and they can kind of be interpreted like regular residuals. And so in this case, we would think that we would want variation increasing with the mean, but that doesn't appear to happen. So a common, to me it's kind of looking a little like that. And if and I think just to highlight this, let's go back here. We kind of, with the Poisson, you expect variation to be increasing with the mean. It doesn't appear to be really happening in this data set. A very common way to account for some amount of model misspecification, even though you feel like you've got the mean model correct in statistics, is to use these so-called robust standard errors. One thing you can do in this case is you could always try the instead of family equals Poisson in the model, you could do family equals quasi-Poisson, and then it will add a multiplicative factor, so the variance is not just equal to the mean, but it's the mean times a factor. That may or may not be the it's not 100% clear that would work in this case, but a general thing that you can do is in statistics is to get kind of these so-called robust standard errors, and Jeff found this answer to this question in Stack Overflow, where you can use these so-called sandwich variance estimates and get a confidence interval that uses these so-called model agnostic standard errors. The process by which this works is basically it tries to get a very general estimate of the variance that isn't highly dependent on the model, with the exception that maybe the mean relationship is specified correctly, and then it forms your confidence interval, and it uses asymptotics to uses the assumption of large sample sizes to get a confidence interval that's robust to model misspecification. Your model doesn't have to be Poisson. What you really need is you need to make sure you got the mean model correct, and you need large sample sizes, and then these will give you kind of robust standard errors. This is the basis for a lot of different techniques in statistics. Okay, and so here we plot we give the confidence intervals for the computed in the normal way versus the confidence intervals computed using these robust standard errors, and you can see the lower limit is a little bit lower than the lower limit calculated normally, and the upper limit is a little bit larger than the upper limit calculated in the normal way, and so it robustifies the standard errors. It makes the intervals a little bit wider. Also remember, these are very small numbers, so if we can do our quick exponentiation and say, we're throughout we're kind of estimating about a 0.2% increase in web traffic per day. Okay, let's talk about modeling rates. So what if you wanted to look, I made a mistake earlier, the simply statistics column is just the count of the web visits that are purely from simply statistics, okay? So imagine if I wanted to model the percentage of total web hits that were from the percentage of total web hits that are from simply statistics. So I wanted to kind of condition on the total number of web hits, and I wanted to model the percentage that were from simply statistics. So this is the expression that I'm interested in. I can log both those sides. I can log both sides, right? And I want it to be a log linear model. And then I can move this log number of web hits on the other side. So what's the result? The result is that we have we model our log count, so the count of the number of hits from simply statistics, and we put in the log total number of hits as a term without a coefficient, so-called offset. If you have some sort of monitoring time or anything like that, you put that in as a log offset, and then your interpretation of your Poisson mean is then the Poisson mean relative to this quantity. Okay, so if you put in time, if we had simply put in log 24, then all of our previous results would have been in the terms of the intercept, for example, would be interpreted in terms of number of hits per hour rather than number of hits per day, assuming a Poisson model about the way in which hits accrue at the site. So in this case, the outcome will be interpreted as expected number of log of the expected number of hits. Well, let's go back to this guy. E to the beta naught, for example, will be the expected number of hits originating from simply statistic out of total number of hits at day 0. Okay. So here it's pretty easy to fit. You can put the offset. You can put it in as a comma offset, or you can actually put it in the model itself. You can actually add plus. You can actually add a plus. You can actually add a plus, and then that variable, if you wanted to, would give you the same result. Either way. Since it doesn't matter, let's leave it like it is. Also, Jeff says data equals G data, so you don't really need that guy and that guy right there. Okay. And so now we can model the count of the hits to his website originating from the Simply Statistics website, the other website that he writes. Okay. And here he's plotting the fitted means in blue, but these are the fitted means originating from Simply Statistics, and here in red is the overall count. The original, see this is, I'm sorry, so if you didn't notice, that was GLM1 for the red one. Okay. Oh, and I should have pointed out, because the visits, again, because the visits have zeros in them, he's modeling not relative to visits, but relative to visits number, not relative to total visits, but relative to total visits plus 1. Here's the rates, so not the count, but the rates. And what you can see is this, so the rate of hits from simply statistics was basically 0 for a while, and then it went up, and the model, fits it as not exactly 0, but close to 0, and then shoots up. So that's our rate model, and that is now that's plotting the fitted values minus the assumed rate at that point. Well, in this case, the fitted value divided by the number of visits plus 1 in this case. So yeah, there we go. And here is the fitted values divided by the number of visits plus 1. Okay, so that's how you model rates in R. So it's just a function, or in Poisson models, it's just a function of adding an offset being a term that does not have a coefficient, and you want your offset to be the log of whatever you want to be in the denominator of your rate equation, and then the Poisson model will R will just kind of take care of the rest. So don't forget to log it, right? That's one thing. Don't forget that 0 and negative values are going to cause a problem for you, and otherwise, this is an incredibly useful thing, this modeling rates using Poisson models. Okay, so some more information. Jeff gives some links on log linears and multi-weight tables. That's a whole discipline in and of itself. Maybe not the most relevant for data science concentration, but for things like biostatistics, it's a very important topic. Wikipedia has a nice article on Poisson regression and a nice discussion of so-called overdispersion. This tutorial, and then there's this problem occasionally that you have the 0 count is sort of more than the Poisson model would kind of expect would look something like that, right? And the 0 count has this extra amount in it that the Poisson model wouldn't anticipate. And you might think in this case this might happen, right? That you have a lot of more 0 counts maybe early on than you would expect, or something like that. And this is called zero inflation. Zero inflation. And there's a fun set of models called zip models. Zero inflated Poisson models that you can use. And there's a lot of different ways to account for 0 inflation. There's a lot. I like zip models, I think, just because I like the word zip. But this is a problem that frequently occurs with count data, and so it's something to be aware of.